This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
We're moved on to the demo portion of my program, and we're going to demo a number of different teaching tools that you can bring right into your classroom with very minimal preparation. One of them is called Seismic, and this runs on a Macintosh computer, and it has an accelerometer built into the computer, so it is showing us vertical motion, XY motion, and X motion and Y motion. And Timmy's going to help us here to figure out which one is the vertical, which one is the X, and which one is the Y. So let's shake the table kind of up and down. Can you help me by grabbing on that side? Which one do you think is vertical? They all seem to be moving, huh? So it's hard to really figure out which one. So let's try holding onto the computer ever so gently and pulling it kind of up and down. Can we tell which one is vertical?
This one.
That's right, the top one. Now let's figure out which way is X. Hold on to the computer with me and we'll go back and forth. Which one is X? Middle one. And now let's go this way.
This one.
That's right. So you can have your students, maybe not with a new computer, but with an old computer, figure out. Now, what are some of the things that we might measure with an earthquake? High frequency?
Yes, high frequency.
So high frequency is when it's boom, and then it's over. And low frequency goes on and on, just like surface waves. Now, here's a seismic station, and we don't have enough battery power. We're only going to be able to run it 12 hours a day. How are you going to know when to run it? Would you run it 12 hours and hope that you get an earthquake then and then turn it off?
Solar panels faster.
Oh, that's a good idea. Someone suggested we get a solar panel. Well, great idea. So that's another thing to think about. I was out on an aftershock study once, and we had the data recorded to disk, and we ran out of space on our disk. So what do? Do you take it offline and run and dump that data and then come back? Or do you send the person to the computer and store, get a larger disk, quick, and hope that there's no aftershock? So one thing you can talk to your class about is what are we recording, how much data are we going to save, etc. That's okay, he's demonstrating. We're obviously in a very seismically active zone, huh? Now that doesn't go on the computer. I often bring these to my classes, and people will say, well, what is that for? And I just set it there, and I say, well, if I need it, I'll have it. And they pay attention. I try not to use it until the very end. And they pay attention, waiting, when is she going to use that thing? When is she going to use that thing? So there's a big earthquake, earthquake. Oh, your station went down. Oh, darn it. We're missing all this great data. Hopefully you guys had your Seismacs running. Oh, we're back up now. Oh, it's going to take a while. Where'd it go? What's going on? Oh, our seismic station is down. Oh, no. So you can go through those kind of exercises. Just like
I just got it back on.
All right, our technician is on it.
That was easy.
So you can imagine there's a lot of things that we can do with this. Is there any questions about this? If not, we'll move on to our seismic building.
How do we access that?
So in the web links that I gave you, on top there's something called hands-on teaching tools, and any kind of thing that I'm demonstrating here will be on that hands-on teaching tools. This one's called Seismic, and it's the first one. I tried to order them by not importance, but of interest to me. Can you go ahead and shut down our seismic station by closing that? Thank you. Now we're going to move on to a building structure. Timmy, you can stay here too. Do you want to be the earthquake or the earthquake engineer?
Earthquake.
You want to be the earthquake? Okay, I need you to stand over here. Hold on to the bottom with me. Earthquake. Let's get rid of this. So how are the people in the building? They're pretty okay, right?
Yeah.
Okay, well, I'm a seismic engineer, and I go, well, you know, I used way too much material in that building. I could probably take some of that off and make a different building and not charge for that. Yeah, that's a good idea. So I'm going to just start, taking off some of this retrofitted stuff because we don't need it. Okay, let's do another earthquake. Hey, this is still good. I can build a whole nother building. Let's take off some more.
If we keep doing that, it'll eventually not have its structure.
Okay, let's try it now. Go ahead and earthquake. Uh-oh. And let's move it the other way too. So now just hold on to the bottom, not on the sides, because earthquakes don't touch the sides, they touch the bottom. There we go. So, okay, enough of the earthquake. That was a big one. That was a long shaker. So this one you can demonstrate what is it for seismic fitting and how good the codes are here in California.
It needs the structure to survive.
It does. So you know what? Can you put this back together for me? I'll let you go sit in that chair there with these and put it back together for me.
Yeah. Okay.
There are these. Okay, I have my seismic engineer on the job. So one thing this demonstrated, where's my other one, is things like in Haiti where they don't have building codes, they would probably not have the proper structure. But here in California and in the US, we have certain seismic safety codes that are very well adhered to, and so we know that when we're in a building like this in California and we get shaking, that we're probably in the first case when we had all our struts on. So that's our seismic building program. Any questions about this one before we move on? This was actually made by a grad student. It took him a long time. The materials probably cost about 60 to 80 bucks for one building, and then his time would probably put it at $250. So we're really happy to have these. Let's do this one while we're here. This is just simple silly putty. A lot of people get confused and they say, well, how can LA shake like a bowl of jelly? It's hard rock. And how can hard rock have seismic waves? And they're just very confused that something so hard can have seismic waves. And one thing you want to put together about this silly putty in terms of the Earth is that even though it's a rock and a solid, you can think of it as a fluid. So we'll put this here, and if somebody wants to note what time it is. Are you guys hungry? Maybe we should do the Snickers next. Anybody? So you can get these Snickers out, and these are going to help us teach about plate tectonics, the 3 types of plate motion. So let's go over that first with yoga blocks. I use the yoga blocks because they make a lot of noise. So when there's 3 types of plate tectonic boundaries. There is strike slip, where the faults are moving past each other, convergent, where they're coming together, and divergent, where they're pulling apart. So which is this? Okay, a little bit louder.
Convergent. Strike slip. Divergent. Convergent. Divergent. Convergent. Divergent. Convergent. Strike slip. Strike slip. Strike slip.
You guys are slow. Okay, you're going to have to pick it up. So you can really get going with the kids. You guys want to try again, or you get the idea? Okay. You can use transverse also. So for the Snickers, you have to check and make sure everybody in the class can have sugar. I usually go ahead and give them out these really tiny, teeny ones. And then I reach in my back pocket and I say, now I'll get the teacher version, and you can get one of those Mambo ones. And those are better to demo with. My husband ate my demo version though. So these, we're going to do the same idea. If you take your fingernail, if you have one, and just kind of dent it a little bit. The first thing you want to demonstrate with your Mambo one is divergent. So take either side and slowly pull apart. And then you can do convergent, where you push together. And one thing to notice with convergent is that you're forming mountains. So on Earth, when you see big mountain ranges, you know there's probably some kind of convergent boundary there. And strike slip is a little hard to do. It's not really changing the topography much. Let's do some Slinkies. So you've probably done Slinkies in your classes. You can stand on this side again. And the thing with Slinkies is, with a class, is you want to have big motions. So you hold this end, and you hold still, and I'm going to be the P wave. So a lot of people demonstrate. There's the P wave, it's compressional. There's the P wave, it's compressional. And here's the S wave, and it goes back and forth. Well, the students are going to get bored. So we want big motions. Okay, hold tight. Ready? P wave, P wave, P wave, And if you notice, he's flinching every time. So this is actually a good height to demo. And are you ready for an S wave? Hold tight. It works better on a large table. So when you're using your Slinkies, you want a large, large motion. You can also ask them, okay, hold on, Earthquake. You can also ask them which moves faster, P wave or S wave. And they'll often get it wrong because they see a lot more motion with the S wave. But because there is more motion, the Slinky's going, oh, I gotta go over here and there and back, that the P wave is actually the faster one.
But since you said that, that's why I got it right.
Oh, I bet you would figure it out with some trial and error, just like a scientist, huh? So here's our silly putty at 5 minutes. Let's go to this hazardous looking thing next. So this is the Earth ball. This is also on the web page. You can get simple modeling clay like this, and I thought you had to search low and high and go to some fancy art store. They have it right at Rite Aid or your basic drugstore. You want ones that have different colors is helpful. Here we have some yellow, green, blue, and red. And you're going to measure these out according to how much volume is in the Earth structure. And then you can put your Earth together. So you start with the inner core in red, then you put around it the green, the outer core, and then the mantle and the crust. And most times people have to cheat with the crust because this isn't really enough to get you around. So the point here is to show, wow, that crust is really, really thin. People think of the crust of the Earth, they think, oh, some gigantic thing. But if you think of an apple, that thin crust of the apple, that's kind of like the thin crust of the Earth. So now when you put it together, you're just putting it together as a ball. So you have the middle, and then you form the others on the other side of it. And to cut it, we've been using this very hazardous thing, but somebody pointed out that we can just use simple fishing line, put it up on a block, something like this, and then take your fishing line and cut through it, and then you can see the different parts of the Earth. Any questions on this one? You can also compare it, have all the students do it, and then you open them up and they're slightly different. And you can see who cheated on the crust and things like that. That's that one. Let's see, what have we not done yet? This I always say, this is my favorite Christmas gift to give out. This is just a simple whistle. I haven't tried it in a while, dare I? So, whoa. In the Turkey earthquake, there were a lot of people that needed assistance, but they couldn't yell for help because help, 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 no one could hear them. A whistle like this is going to be heard by a larger radius. So this is my favorite thing to give people for Christmas, just to have around for safety. Do you want to have 3 volunteers for this project? Okay, we'll just have Timmy. Can you stand over here again? Okay, pick your favorite color. Okay, so we're going to blow up these balloons just a little bit, like this. So I say it now, got it a little bit, and then hold it tight so we can hold it up and show people.
I can't do that.
Okay, we'll let somebody else try. So now we blow it up a little bit, and this is an earthquake prediction. So if I keep blowing, eventually this is going to pop, right? So tell me when it's going to pop. Does anybody think it's going to pop now? No. Now? Now? So you can just do this. In fact, you can have a lecture where you have one of those balloon ties, and you can just tie it off, and then every now and then go by and go. Etc. And then you're waiting, is anybody going to predict when this is going to pop? So this is a relatively easy thing to predict. We know when it gets big enough, it's going to pop. So I'm too much of a wimp to actually blow it until it pops. As you saw, I had trouble blowing the whistle. So what I do is I get it big enough to where it might pop, and when I'm talking, I have a pin, and I pop it. And so no one's going to predict that because they don't see my mouth here. So there's other stress perturbations that could come upon the balloon, just like other stress perturbations could come along our earthquake faults. So that's a simple way to use balloons. I did talk to one teacher who actually blew it up until it popped. That was a Friday, though, and he said he didn't do much on the Saturday. So next we're going to do a plate tectonic puzzle, and Timmy's going to help me put it together. Usually what I do is I give every student a piece. If there's not enough students, then if there's too many students, we can double up. So these are all cut by the plates. So how I made this is we start with a gigantic map called this dynamic planet map. And there's a template that you can use to cut out the entire plates. And then you have to laminate it. And the drag is then you have to cut it out again. There's also a number of very small plates. So you probably want to have a special envelope to save those little small parts of the plates. So while he's working on that, I want to show you one thing you can do with the Pacific plate. Oops, I grabbed the wrong thing. Go ahead and work. Don't let me distract you. So I often teach this in the summer and go, wow, it's hot. Is anybody else hot? Who's the hottest here? And say, okay, you're the hot spot. And you give them some kind of laser light like this. So just a simple laser light like you might use in a presentation. And this is going to be your hot spot. We'll find the Hawaiian Islands. I wonder if this is going to show through for you. Can you see that hot spot? So the hot spot started here. And as the plate, let me see if I can pull it. As the plate moves, the new islands are formed. And here is our current island that's active here in Hawaii. So again, you can just hold the hot spot on the bottom, and the person being the hot spot has to hold still, and it's the person with the plate that has to move. The plate's moving, not the hot spot. Oh, you probably need this. Here you go. So a globe like this is good for a number of things. You can just refer to it if you're talking about scale, etc. I like to use this one if we have a global earthquake in San Diego, and we can, a global earthquake somewhere in the world recorded in San Diego. You can look at those data, and just one seismogram, you can use that equation, the P arrival minus the S arrival, the time difference between those two in seconds, times the number 8 is the kilometers away. So here we are in San Diego, and then you can translate that to some kind of measuring device. You can use a ribbon, you can use one of those cloth tape measures, something that seems to be measurement tool rather than a ribbon sometimes works best. And once you know what that distance is, then you can say, oh, we know it's somewhere here. And so you can say, well, do we think we have earthquakes out here? No, probably not. Oh, it could be in Haiti. That's one possibility. You could swing around, oh, not much seismicity out here. Come all the way around on this side. Oh, could be in Alaska. So Alaska has a lot of earthquakes. Maybe it's there. So you can just give the students, here's a seismogram, figure out how far away it is from your seismic station, and then just by swinging around here, make an educated guess, where do you think that earthquake was? Now, since we had a large earthquake in Haiti, sometimes people would say, well, since it does match up with Haiti, maybe it's an aftershock of the Haiti earthquake. That's a good reasoning. So test their reasoning skills in terms of where they think it might be and why. How's it coming? So one thing that Timmy's run into here is that the world is a globe, right? And so some things match up on the other side, like here. This matches here, but it also matches up on this side. So it's confusing. Do I put it on this side or that side? And Timmy's decided it matches over there better from that. We can also use the globe to say, well, Australia looks like it falls off the edge there, but we know from our globe that it continues. So make the connection between the globe and the flat map. Let's see. How about these big pieces? Here's an edge piece. That's an easy one, huh? There we go. Okay. So once we get our plate together, some things you can point out is it's not necessarily at the edges of the continent-ocean boundaries. Like there's no plate here on the eastern seaboard of the U.S. You can also point out that in Iceland, it goes right through Iceland. It doesn't go around Iceland. So when you cut it out, make sure you do that. You can also see that the subduction zones, the regions in high with the red, are the regions that are subduction zones where there's mountains. So where there's mountains, there's almost always a plate boundary. Where there's mountains, there's almost always a plate boundary. Where there's mountains, there's almost always a plate boundary. So ask your teachers those kind of things. So let's move to these maps. One thing you can do is you can go to the IRIS webpage and say, where were the earthquakes today? And have the students go up and put red earthquakes, red circles for the larger magnitude earthquakes, green circles for the smaller ones, and maybe yellow for the even smaller ones. And over a course of about 3 months or so, you're going to fill up and actually map out some of the plate tectonic boundaries. Now as a teacher, you're going to want to keep some of these stickers on your own because you might have to go in and add a few on the weekend just to get the point across. But in general, this is a good way for them to figure out, number one, how to figure out lat and long and where that earthquake might be. And then they also kind of start looking at it and go, oh, well, here's my lat, here's my lawn, oh, it's probably here with the other earthquake. So they're starting to use reasoning in that way. So this kind of put the stickers on the map as another good mapping tool for teachers. And I think that's it. If anyone has any questions, feel free to ask me. I'm here to help.